Are there any questions?
Yes, I have one. I'm pulling it up right now. It's from the master setback.
Oh. Just realized I left something in my office. Okay, your question first.
In the diagram below, the AC power supply cycling at 60 hertz, the resistor at 20 ohms, the capacitor at 50 ohm per nanofarads, and then the inductor at 50.2 millihenries. I just needed you to do the first one. What is the reactance for the capacitor and the inductor? It's just an AC circuit with.
Yeah, let's see if I have an actual copy of that. Nope. There. That's not there. All right, I'm gonna have to see it. Number 6.
You're also supposed to have it to see the diagram.
All right, 2 circuits, same plane.
No, that's
Oh, no, 6, not 7. In the diagram below, or to the side, so it's an RLC series circuit.
I just wanted help on the first one, the reactance and across the resistors.
Oh, reactants, okay. All right, I don't need the numbers. Capacitive reactance is 1/omega C. The inductive reactance is omega L. So if you know omega and you know the inductance, just multiply it. It's just straight plug and plug to a formula.
What? We know is the inductance the inductor of the 50.2 henries or millihenries?
The 50.2 millihenries would be the inductance.
And then you just multiply that by the frequency that it gives you.
Angular frequency. I gave you the regular, I just gave you frequency, right? I gave you F equals
The AC power supply is cycling at 60 hertz.
60 hertz. All right, that's F, not omega.
And then you just do 2 by 5.
Yep, exactly.
Thank you. I just wanted to refresh.
And Ibrahim just got an alibi.
Well, Ryan included it.
Or wouldn't, because he has an alibi. Or maybe I just won't post it. No, he wasn't here that morning.
He emailed me saying he was doing crime, so I couldn't come inside.
All right. It's a question. I'm gonna grab something from my office. May or may not use it, but. All right, we last left off. Oh, any other questions? We last left off with talk about the Rossi-Hall experiment, and I realized that I had there's 2 major experiments that were done that were very similar to each other, and I was mixing and matching them, so we're gonna sort of start over all that. I didn't get very far to begin with. All right, so Rossi and Hall, 1940. Or Hall and Rossi, I guess Hall went first. All right, so they set up 2 detectors. One in Echo Lake, elevation 3,240 meters. And potentially set up another one in Denver, Colorado. I think Echo Lake is in Colorado, but generally the literature just says Echo Lake. I think everybody knows where that is. Elevation 1616 meters. All right, so they are looking at this particle called the muon. Now, a muon has a half-life of 1.56 microseconds. So muon, generally symbolized by the letter mu, which may or may not be in the do not confuse these mu's, but typically you have either a plus or a minus as a superscript to indicate you're talking about a positive muon or a negative muon.
How do you spell muon?
Muon.
Just how it's spelled.
And the half-life of the muon is 1.56 microseconds. So, not a whole lot of time there.
Quick question, and it might be out of the scope of this course. If they only last for that amount of time, how are their muons still existing?
Because they're being created also.
Do we know how they're created?
Yes.
Okay.
They're coming from the sun, and we get a small fraction of the ones coming from the sun. You just need, in essence, we can create muons just by taking some target and smashing tiny particles into it. When I say tiny particles, I'm talking, I got some carbon target, and I shoot protons at it near the speed of light. And what comes out of that, you get a shower of particles, including some muons.
Okay. Wasn't that your dissertation?
Yeah, that's why I use that as an example. Now, I didn't particularly look at muons, I looked at a different particle that came out of it.
The blue one?
The what?
The blue one?
The blue one? No, I wasn't down to the level of colors. So we're gonna Fred, the particle.
The big one?
Medium size. I was looking at a particle that was roughly, very crudely, size of a proton, called the lambda c. The famous lambda c, that's right. Okay. All right, so they looked at the number of these muons that were coming through at that point and at that point, and they found that at Echo Lake, they had on average, 348.6 muons per hour. So the question is, how many should they see in Denver, Colorado? Now, part of this is, we're constantly getting bombarded by muons, they decay, and what they decay into is some neutrinos and an electron. Well, let's take a look at it from two different points of view. We'll start out with the non-relativistic, as if Einstein was wrong, and then we'll take a look at if Einstein were right. That's going to take a moment. All right, so the distance that it travels, and recognize that it's not like the muons here are going to get to here. These are different sets of muons, but you're looking at on the average that we're getting bombarded by muons, and all you need to do is look at it from this elevation and this elevation. That at the same time of day, you will get pretty much the same number of muons per hour no matter where you are, the same elevation, same time of day. All right, so it is going to travel, well, the difference between them. Doing the fancy math here, that's 24 meters. I did the math right. Now the muons are traveling at a speed of, there we go. The speed of the muon they found was, we're more sophisticated than just the V there, beta, 0.997528. That is on average. So if it's traveling that times the speed of light, how long should it take the muons to get to here? Or to travel this distance? Well, how do you find time? If you know speed and distance.
1 over the, well, because we have a formula, but I feel like this has the relativity part in it. Because it's the T equals TP over,
Oh, you're going way sophisticated here.
oh,
So first off, we are solving this the first time, assuming relativity is bunk.
Time over velocity.
Time over velocity.
We're trying to find the,
We're trying to find time if I know speed and distance.
oh, distance over speed.
Yeah.
that's what I was
Live. It claims it's yellow, is it actually? It is. All right, so I know that time is distance over speed. So the distance it's going to travel is 1,624 meters. The speed is 0.997528 times the speed of light, which is about 3 times 10 to the 8th. And what do we end up as with time?
.42679.178 times 10 to the negative 6.
So it rounds off 5.43?
Yeah.
Okay. So 5.43 microseconds. So now I know what the half-life is, 1.56 microseconds. Let me just make sure that that is indeed half-life and not mean life. Okay? So when you're dealing with exponential decay, that the number of particles is equal to what you start with times, not E, since we're doing half-life, 1/2 to the T over the half-life. So we can calculate how many particles should be existing down in Denver if relativity is bunk. So we have 348.6 times a half-life of 1/2 raised to the 5.43 divided by 1.56. And we end up with
31.225.
or on average 31.225, or roughly somewhere around 31 muons. So if relativity does not have any bearing whatsoever, we should have only 31 muons hitting Denver per hour. Questions to hear?
Is this anywhere in Denver?
Yeah, pretty much. I mean, it should be pretty much whatever time of day they were doing that, how many we're feeling.
And does it depend on weather? If it's cloudy?
I don't think so.
They
I think the nuance would go right through it.
How big are their neons?
Probably on par with the size of an Electron.
So huge.
So huge. If you're a quark, maybe. Although electrons probably are smaller than quarks. Never mind. All right, so what if relativity is true? Well, if relativity is true, then obviously we're going to get a different number, otherwise this would be a completely worthless exercise. Let's see how much time would pass for the muons. We have, I know that time is equal to the proper time, I'll put the gamma first, equals gamma time proper. Proper time being in the rest frame of in the rest frame of the muon. Well, sorry, wait back up there. It's been a long weekend. Proper time is the amount of time that passes for the object at rest. So from the muon's point of view, they're at rest. So gamma, well, let's first calculate that. Gamma is 1 over the square root of 1 minus beta squared. So that's equal to 1 over the square root of 1 minus 0.99758 squared. And we get,
I had a question. By the rest time, do you mean like if I was a muon?
right?
It's like sitting in a car looking out the window and everything else is moving but you're not?
Yes,
Okay.
exactly.
Even
There
if
you
you, sorry.
14.23.
All right. So, well, there's two ways of looking at this. Why don't we do it from the point of view of how much time passes from the muon's point of view? So we figured it would be 5.43 microseconds is the amount of time from the scientist's point of view. So 5.43 is equal to 14.23 times the proper time.
So do the division, and you get 0.381.
All right. And that is, yeah, that is microseconds. So from the muon's point of view, if special relativity is true, from the muon's point of view, only 0.381 microseconds passes. And by that, we end up with n is equal to 348.6 times 1/2 raised to the 0.38, that is an 8, yeah, 0.381 over 1.56. And we end up with
Really, guys? I'm the only one doing this.
you and Jack, I think, are the only ones with calculators out.
The Ethan's not here.
293.66. He's just waking up. Give him some time.
293.7?
Yeah.
You get the same thing, Jack?
Is that 1.56?
That's a 1.56.
Oh, hold on. 1.56.
I got 294.
Yeah, that's. I put 2 for some reason. 1.45.
Not 293.7, but 294.
294.31.
Yeah.
All right. Per hour. So we got a very clear difference here between what should be, how many muons would be predicted at the bottom. And what they found was, so I'm doing they had 2 different experiments, that's why I'm pausing here. Not that number. Oh, there we go. 248. They ended up with 265. So that's the experimental, that's the prediction, this is the other prediction. So clearly, it is so much closer to that than it is to this one. This was the first, this is 1940, this was the first real experimental evidence that special relativity was true. Now, there have been little glimpses and clues of the fact that something else was going on. However, this was considered one of the major experiments.
So they did this experiment by having this clear box of, you said superheated liquid last time?
Yep.
Which basically means if anything, even tiny little particles go through it, it makes bubbles.
Yes.
And then they just stood there and watched, counted how many bubbles they saw.
That's why graduate students exist. They might have had more sophisticated electronics than that, but that bubble chambers were coming into being about this time. So, if special relativity is true, then is there anything that's the same? We have 2 different points of view. We have the muon's point of view, and then we have the Earth's point of view. Do they agree on anything? We have 1 vote for nothing. Well, let's take a look at I've got my detector up here, I got my detector down here, this will be Denver, this will be Echo Lake. All right, so from the Earth point of view, Earth point of